So try to recall, FSK has two different signals and they have two different frequencies, right? Symbol 1, we are sending S1 of t, which is going to have a frequency component of F1, and symbol 0 is, right, you are going to send S2 of t has a frequency component denoted by F2. Both functions have the same amplitude, but the frequency components are different. The first signal has cos 2 pi F1t, second function has cos 2 pi F2t. Right. So now the condition is that how many basis functions do you need? So if you compare this with, yeah, sorry, two basis function, obviously, because if I write cos 2 pi f1 of t as one of the basis function, like we did for ASK, PSK, now you see that here I cannot use the same function for the other one. I need to use a different one, right? So because of that, we need to choose the what you call basis functions differently. Okay, right. So we need, directly I'll write this. This implies we need to two basis function. Okay, so let us try to define them. The first one is phi 1 of t is equal to, see, the energy bit comes from the symbol which you are setting. Other than that, whatever you have, you need to write here. That is, oh, sorry, it's not minus. It looks like a -2, but see to that it's not minus. Okay, this is 2 divided by TB into cos 2 pi f1t, right? So 0 less than or equal to t less than or equal to t. So this is the phi 1 function. Similarly, you are going to use the second function, that is phi 2 of t is equal to root of 2 by tb into cos of 2 pi f2t 0 less than or equal to t less than or equal to t. Okay, now if you want to represent S1 of t, you should use phi 1, correct? If you want to use the S2, you should use phi 2, right? This implies, now let's try to write that. So if you want to represent S1 of t, you have to multiply that with the energy of that is EB, root EB into phi 1 of t. Are you okay? When you multiply by root EB, you get this. Right? At the same time, let me try to write the S2 of t now. Right? This also implies the S2 of t is nothing but the same root EB is the amplitude, but I'm going to multiply with the phi 2 of t. Are you okay with this? Right. So, you see, we can try to consider the FSK as two different ASK signals, right? So it's because let's try to write the what you call the constellation diagram. Okay, the constellation diagram is going to have two different axes, right? If you remember the ASK signal, right? One symbol is 0, other symbol is root E, correct? This is along a phi 1 axis. At the same time, you consider another axis like this. Okay, so say call this is phi 2 and mark another root EB over here, right? You see this becomes the FSK, right? Because root EB remains same. Both the functions will have the same amplitude. Only the axis where you try to mark the root EB is different. Are you okay? Right. Anyway, I'll come to that point. This is just a heads up, right? About what we are going to see. Right now. So the two different what you call axis we have chosen, they are something like orthogonal to each other, right? So orthogonal to each other means if you take a product and integrate of phi 1 and phi 2. So I'll write a point here. This is a note, right? So the phi 1 and phi 2, phi 1, so the phi 1 and phi 2 are orthonormal. So what do you mean by orthonormal? If you integrate the product phi 1 and phi 2, right, that gives you a answer as 0. Okay. And if you integrate phi 1 into phi 1, that gives 1. That's also equal to integral of phi 2 into phi 2. Phi 1. So phi I into phi j is 0, but phi I square or phi j square is equal to 1. So any function which satisfies this condition, any phi 1, phi 2 will be regarded as the orthonormal functions. Okay, orthonormal. So there is a term ortho indicating that they are perpendicular to each other. That's why I told, right, we are going to draw the phi 1, phi 2, right, at 90 degrees to each other. Okay, fine. Before that, anyway, we are going to draw that now. But before that, we need to mark the points, right, on some places, right? So let us try to do the calculation, right? So since there are two message points, since there are two message points, right? Each of them are represented by the signal vectors S1 and S2. So 2 points represented by S1 and S2, right? We need to calculate the coefficients of signal on S1 as well as S2, right? So we will calculate the coefficients like this, right? So we need to calculate, we need to calculate the coefficients of say S1 of t, right? There are two coefficients. How do you write that? First one is S1. S11 is nothing but, you see the same equation we used earlier, that is integral this. So S1 was my received signal. I will try to capture its image on the first basis function phi of t into dt. So how do you represent this? This is nothing but actual signal, that is root e, right? But you see, if I try to write the S12, this is going to be 0 to tb, right? It is S1 of t itself, but on the other signal, that is phi 2 of t, right? Are you using phi 2 of t for S1? No. So this gives you a 0 because it's perpendicular. Phi 2 is perpendicular to the, wherever you mark phi 1, that's the other component is perpendicular. That's why you try to write this. So what means, this means when I try to write S1, I use the coordinates root EB, that is along the first axis, and 0 for the second axis, right? This is the what you call as the coordinate representation. Now you see this is two-dimensional. That's why I need, every point needs two values like x comma y. On a xy plane, if you mark, if you want to mark something, you need to have two coordinate values, right? Like that. The same concept. Now, but now I don't have x and y. I have phi 1 and phi 2. So how much distance you need to move along phi 1 to reach S1? That is root EB. How much you need to move along the phi 2 axis? It is 0, right? So that's what is the meaning of this. Similarly, I need to calculate the coefficient of S2 of t. So I can write, similarly, the coefficient of S2 of t right? So S2 of t should be calculated in the following similar fashion. So first let's calculate S21, right? That is integral 0 to tb. This is S2 of t. Multiply this S2 with phi 1. So there is a dt here. So that is equal to 0 because S2 is marked along phi 2 and I'm trying to multiply that with phi 1, which is orthogonal, right? Similarly, S22. S22 is integral 0 to tb, right? S2 of t. What is S2 of t? It's a second signal into the phi 2. So since both of them are marked on the same axis, this gives you an answer root EB. Are you okay? So how do you denote the point S2 now? This means any point I want to mark on S2 should be 0 on phi 1 and root EB on the phi 2 axis. Is it okay? Right. So now using these 2 points, right, we will try to mark both the points on the constellation diagram. Okay. So let's try to write the constellation diagram. Right. So you see this is the phi 1 axis. This will be the phi 2 axis. So this is 0. Right. Now let us say I want to, so this is in a sense its origin 0 comma 0. Phi 1 is 0, phi 2 is 0. Let me mark a point here that is equal to, right? I am moving along phi 1 first, that is equal to root EB, and I am not moving any distance along the y axis or the vertical axis, that is phi 2, so this is 0. So what is this point? Root EB comma 0 is the S1, right? So at the same time, if I mark a root EB over here, right, this coordinate will be 0 comma root EB. We are moving 0 along phi 1, but root EB along the phi 2. So this has to be the point S2. Is it fine? Okay. Now, where should be the decision boundary? Where do you find out that, okay, this has to be the decision boundary, so that one side of that will be S1, other side of the line you are going to draw is the S2. So always this should be somewhere in the middle, right? So how do you decide the midpoint now? So in order to decide that, you need a midpoint, correct? So how do you define the midpoint? Let's try to connect them. Maybe like this. I'll try to put an arrow between them. Now you see somewhere at the middle, it's always the midpoint which decides, right? So let's say this is the midpoint. So if this is the midpoint, always you try to draw a straight line passing through the midpoint. Now I'll try to make sure that it also passes through the origin. Okay, let me try to extend this further like this. right? So this point, midpoint is, okay, let's call this as a decision boundary. So what is this line? It's actually going to make 45-degree with this because it's passing through the, it's bisecting the first quadrant, right? So that is denoted by x1 is equal to x2. Right. Now, how do you decide which region is what? Anything which falls below this will be the, right? So I'll change the color, say this whole region. So if that is a decision boundary, anything falls on this side, right? This complete side, right? We'll try to denote that as region Z1. Okay. I'll also mark another region on the other side, that is this complete side, the other half, right? So let's try to denote this region as the region Z2. Now, using say, what is the condition? How do you recognize a point is in the region number 1 or region number 2? How do you identify? What should be the condition? So, like my question is like that. If I had something like this, and right, if I say this is region Z1, this is region Z2, maybe this is the center. I used to call that if x1 is greater than 0, that is Z1. If x1 is less than 0, that was Z2. Okay. Yes, yes, yeah, yeah. Please answer. Perfect. Right. So we try to recognize, right, the or the decision boundary can be used to identify, right, in the following fashion. So in the region Z1, right, what was the condition you mentioned? X1 is bigger, right? At the same time, the region Z2 is recognized as the X1 is lesser than X2. All right. Okay. Now, so anyway, the decision boundary has been defined, and the constellation diagram is actually very useful in that case. All right. Now, so let us go to the block diagram representation and the generation. Generation of FSK. It's the modulator diagram. So we have the binary signal, right? Binary, that is 0 or 1, which is coming as input. So binary wave is coming. Now you see, I have to either multiply that with phi 1 of t or phi 2 of t. That depends on whether 1 is coming or 0 is coming. So what you do now, you try to split this into two parts. Okay, let's try to split this into two parts. The same wave will be split into two parts. Okay, one of the part is taking care of the input being equal to 1. Other part will take care of the input being 0. Okay, let's say input is 1. What you are supposed to do when the input is 1, you need to multiply that with phi 1 of t. Let's say this part of the circuit takes care of the phi 1 of t. So I take the signal is being 1. So simply multiply that, use a product modulator, and what I'm going to multiply to this, I'm going to multiply a phi 1 of t to this. Okay, but when you have the signal coming here that is equal to 1, right? I should not use the other part, right? The other part which is going to multiply with phi 2, right? You should not use it, correct? So what you do, you use an inverter over there. So that whenever this input is 1, right, the other input becomes equal to 0. So for that reason, I'm going to use a inverter here. Okay, so see, this is an inverter circuit. I'll use an inverter. It performs the NOT. So 1 becomes 0 here, right? When this is 0, right, it is not going to multiply. Though I have a circuit performing the multiplication or the product modulation with respect to there is a product modulator and it takes the input of phi 2. This is not going to work because the input is 0 as the other input is 1. So 1 goes here. So the same 1 comes here, but this becomes equal to 0 because of the not operation. Okay, so I multiply by with the phi 2 here. For this example, it is of no use. Okay, so what I can do here, this I can call it as the m of t, right? This becomes the m cap of t or m bar of t. I think m bar is more suitable. So it's a not function. So 1 goes to the upper branch, 0 comes to the bottom branch. At the same time, when the 0 comes as input, right, the upper part will not multiply because 0 goes as it is. But the bottom part will be 0 gets converted into 1 and you multiply. Okay, so after that, I have a summing circuit. This is a summing circuit. So how this works, it's pretty simple. Take the output of this and give it to this. And upper part, I'm going to call that as S1 of t. At the same time, the bottom part is the S2 of t. Take a sum. Either of them will come, not both. Simply take it out. So this is the FSK. FSK. Right. So very straightforward, right? Whenever you want to generate an FSK, you can use a simple concept like this. Okay, that's the modulator circuit. Now let me go for the demodulator circuit. So very similar logic I'm applying here, right? Let me say I receive the signal x of t. Received signal, say denote that as x of t. That comes from the antenna, say that is available over here. So what we do, we split this into two parts once again. One part put top this. So one of the branch will take care of the demodulation whenever it is uh, 1. Other part will take care of the demodulation whenever the part taken is say 0. Okay, so this is one of them. Say this is the other part. Okay, now let us use a product modulator. So one of them takes phi 1 as input and the other one is going to take the phi 2 as the input. Phi 1 of t, phi 2 of t. Now I know that always I have I just have to uh, consider whether there will be two samples x1 and x2. Which one is larger I need to see, correct? That's my logic here. So what I do, I will this is actually a correlator. So correlator circuits are always expecting the integrator blocks. So let me write one integration block here and another integrator block here. So both will perform the same thing. It is integral 0 to say tb dt, 0 to tb dt. Okay, now let's use a summer block. This is going to perform the sum extent. So let's give the notation in slightly different format. So let me call this is, say, the upper part generates x1 and the lower half of the circuit generates another symbol. So denote that as, say, x2. Right? So now I say this is positive, this is negative. It's actually not a summing block, it takes a difference. Okay, so what you get here is, say, let's try to denote that, that is y. Y is nothing but x1 minus x2. Are you okay? So this y is given to the decision device. Right? Now you see our decision is if y1 is greater, sorry, x1 is greater than x2, then the difference, that is x1 minus x2, will be positive. Correct? At the same time, if I want to decide that symbol is 0 if x2 is larger than x1, so that the difference x1 minus x2 will be negative. So I just have to decide whether the y is positive or negative. So what should be the threshold? Can you tell me? What is the threshold that you are going to use so that you can decide whether x1 is greater than x2 or x2 greater than x1? It depends on y now, right? What should be the condition on y? Y is equal to x1 minus x2. What should be the condition on this? Depending on which I can make a decision about whether I can write decision, whether I can make a decision whether the received symbol is corresponding to 0 or corresponding to 1. How do you make that? What is the threshold value? What should be the threshold value? Can you guess? So taking this as 0, right? Decision is made in the following fashion, right? So the output will be decided as 1, right? If the y value is greater than 0, making x1 bigger than x2. This will be 0, right? If y is less than 0. So when y is less than 0, y is a y means it is x1 greater than x2 or x2 greater than x1. That's when it becomes negative, correct? So that's how you make the decision. Okay, right. Now let's go to the receiving part, right? And let's look at the received signal, right? So we'll calculate the probability of error, right? So we start with the representation of the received signal. So that is let the received signal be x of t, right? So if you want to represent in the vector format, so in the vector form, let's try to denote this is simply x, which has two coordinate values. One is x1, one is x2, right? So the value of x1 and x2 you calculate like this. So where, how do you calculate x1? x1 is nothing but you are going to correlate that 0 to tb, right? The received signal, that is x of t, correlate that with the phi 1 of t. That's the upper channel of the receiver, t. And how do you get the x2 value? x2 value is the correlation of this received signal x of t with respect to the phi 2 of t. So that's how we calculate this. Right, now you see what happens to x of t if 1 was transmitted, right? But if we are transmitting the symbol 1 was transmitted, how do you represent x of t now? X of t should be the first signal, right? That is S1 of t plus the noise, that is W1. At the same time, right? If the symbol 0 was transmitted, then the same x of t can be represented as the sum of S2 of t corresponding to 0 and some noise, that is W. Okay, anyway, I don't have to write W1, W2 here because all the noise is same, right? I don't have to distinguish. So it's just W. Okay, now you see, if you want to calculate the probability of error, right, I just have to calculate the random variable capital Y, which is the difference of two different random variables, x1 and x2, right? So where x1 is the symbol corresponding to the correlation between phi 1 and the received signal, the capital X2 will be the correlation between the received signal with phi 2, correct? So let's try to write that, right? So we'll do now. So that means let capital Y be the random variable defined as capital Y is equal to capital X1 minus capital X2, right? So how do you represent then, right? Okay, X1 is the received symbol, X2 is the received other received symbol, right? You obtain X1 and X2 after you correlate with the received signal with the phi 1 and phi 2. Okay, that's very clear. Now, so this implies, and I'll also write their sample values are small letter y, small letter x1, and the small letter x2 respectively in the same order, right? Now you see uh, the sample xi, right? We can try to write in the following notation, right? Let's try to denote in the following form. Okay? Denoting the the sample value xi, okay, when 1 was, this is symbol 1, okay, when 1 was transmitted, right, as this is xi given that 1, right? And what are the I values? I values could be 1 or 2 because x1 and x2, we have two options, right? We try to denote it in this way. This will be the standard notation we are going to follow. So I can write x1 receiving x1 when 1 was sent is nothing but, you see, this is s11 plus w1, correct? W1 is a noise. So what is s11? We already know that this is root of eb, right? Plus w1. At the same time, if you receiving x2 when 1 was sent is nothing but, this is s12 plus w. Maybe I'll write it as a w. But s12 will be 0, right? Because, right, there is no correlation. S1 is x1, S12 is received signal x1 into phi 2. So there may not be any correlation. So plus w. So whenever you receive x1, provided 1 was sent, it is like this. At the same time, I can write it in the, uh, uh, write the other one as x2, given that 1 was sent, is simply w2. Okay, so I'll write, so this is equal to w2. Right, now you can calculate the, what you call, the expected value, right? Let's try to write that. Right, so the first part, that is, this implies I'm going to calculate the mean. How do you calculate mean? The first one, expected value of x1 given that 1 was sent is nothing but, it's a simply root eb. Anyway, we know that how to calculate that. I'll just fast forward our calculation. Similarly, the second one, that is expected value of x2 given that 1 was sent, it is nothing but expected value of the, or the mean value of w2. Mean of noise is assumed to be 0, so that's why it's 0. Okay, similarly, we try to denote that, we already have given that the y is equal to x1 minus x2, correct? So let's try to denote that. So since y is equal to x1 minus x2, I can try to write the mean of y in the following. So that is expected value of the y when 1 was sent is equal to expected value when x1 was received when 1 was sent minus the expected value of x2 when 1 was sent, right? By substituting the previous values, I can directly write this is equal to, right? X1, this is root EB, and the second one is 0. So this is simply root EB. Okay, now this was the calculation corresponding to 1 being sent. Similarly, do the calculation for 0 being transmitted. Similarly, when symbol 0 was transmitted, what happens? Right? The x of t being denoted as s2 of t plus the w of t, right? So try to denote the x1 bar 0 is s21 plus w1. But what is s21? That is 0, only w1 remains, right? Similarly, give a notation x2 uh, when 0 was sent. In the sense, you send a 0, receive a 0. That is s22 plus some noise, maybe w2. Okay, so s22 will be root eb, right? Plus w2 remains as, right. Now you try to calculate the mean value of both of them, right? This implies I'm going to calculate the mean. How do you calculate? The expected value of x1 when 0 was sent is equal to S21 plus W1, which is just W1. So expected value of the noise, that is equal to 0. Similarly, the expected value of the second one, that is x2 when 0 was sent, is nothing but it is simply expected value of, right, the root EB plus 0. So that is simply root EB. All right. Now, also let us try to calculate. Therefore, the y is x1 minus x2, right? So this implies I can calculate the expected value of y as the difference, right? That is the first part, that is 0, and the second part, that is root e. That is equal to minus of root e. Okay, I got a mean of y for both the cases when 1 was sent and when 0 was sent. So I'll try to give a notation here. So I think I have given the similar notation earlier. Expected, E of y when 1 was sent, right? Similarly, I actually have to write when 0 was sent. So this is E of y bar 0. Okay, so there is a y and I have a condition 0 over there. E of y bar 0 equal to this. Also, we can directly write what is the uh, variance, and let's calculate the variance, right? So that is variance of y is equal to, it doesn't matter whether you are adding or subtracting, total variance is going to remain same. Variance of x1 plus the variance of x2, right? Because y is equal to x1 minus x2, but variance gets added. Okay, variance of x1 has a noise n naught by 2, and x2 has another noise n naught by 2. So variance of y becomes equal to n naught. Is it okay? All right, right. Let's proceed further. Only this derivation will finish. Okay. All right. So directly we can write. Now we know that what we are calculating. So the conditional PDF, the conditional PDF, I directly give the equation itself. In the sense, I'll directly give the notation. This is Fy of y given that 0 was sent. This has to be equal to, right? Now you see it's the same 1 divided by root of 2 pi, the sigma square. This itself is a sigma square. Okay, sigma square is n naught itself into e to the power exponential of, right, minus of, now you see the variable is y, so I have to write a y, right, minus, right, when 0 was sent it is minus root eb, so minus of minus is plus root eb whole square divided by 2 times sigma square, which is n naught, right? So this is the conditional PDF. You use the conditional PDF to calculate probability of error when 0 was sent. So what is the condition? This means probability that the y is greater than 0, right, when the symbol 0 was sent from the transmitter side. So that means when the 0 is sent, what is the condition? Y greater than 0. Y greater than 0 means it is 0 to infinity, right? You just have to write that. So this is equal to integral 0 to infinity. Write the function. Function PDF is Fy of y given that 0 into dy. Right? Let us substitute. So this is equal to 1 divided by root of 2 pi n naught integral 0 to infinity. This is exponential of minus of y plus root eb the whole square divided by 2 times n naught, okay, 2 times n naught times dy. So what we should substitute now? So how to simplify this? So we are going to make a assumption here, right? So always we do the same step. So put sum u is equal to that y plus root of eb divided by root of 2n naught. This implies I have to substitute dy is equal to root of 2n naught into du, right? So this means when uh, we need to change the limits. So y actually varies from 0, start from 0. When y is equal to 0, what happens to the u value? U is equal to square root of eb by 2n. And the one y was reaching infinity, the u also reaches infinity. So according to that, we need to make the changes now. So this implies probability of error when 0 was sent is equal to 1 divided by the root of 2 pi n naught integral root of the eb by 2 n naught to infinity. This is exponential of minus u square into, I'm writing du and a root of 2n naught. So this root 2n naught cancels with this, right? With the 2. So what you have left out with is 1 divided by root pi integral root of eb by 2n naught to infinity exponential exp of minus u square t, right? Again, you can see that this is a standard error function. I'll try to denote that as half of error function of the root of eb by 2n naught. That is a probability of error for 0, right? So in a very similar fashion, we can also derive that. Anyway, it comes the same, so I will write. So similarly, I can write the PE of 1, that also going to come the same value, half of the error function of root of EB by 2n naught, right? Assuming the same probability now. So assume probability of 0 equals to probability of 1, that is equal to half. Now PE, probability of error, is equal to P of 0 into PE of 0 plus P of 1 into PE of 1. Once again, it ultimately comes to the same, because half into half is 1 by 4 plus one more 1 by 4. So that ultimately becomes 1 by 2. 1 by 2 error function of root of EB by 2 times n naught is the probability of error of FSK signal.